Okay, we want to now continue our review for the Unit 2 lecture exam by talking about lesson number 4, what magma is and how magma turns into igneous rocks. So in your textbook, this is going to be chapter 4. And first you've got to know, what is magma composed of? So it's going to have ions in it. And so some of those ions are going to be like aluminum and calcium and sodium and potassium and iron and magnesium. And then it's going to have silicates. So if you recall, a silicate is going to be composed of a silica tetrahedron, which is going to be a silicon, and then it is attached to 4 oxygens. And then we said that these silicates, these silica tetrahedrons, could be isolated or they could be connected together into chains or sheets. So inside of magma, you have these silica tetrahedrons. So some of them are isolated, others are in the form of chains. Okay, then you're also going to have dissolved gases in the magma. So they're in the liquid, and so you would not be able to see them because they're under so much pressure that they are dissolved. So you have water, gas, you're going to have carbon dioxide gas, sulfur dioxide gas. Those would be the major ones, and then also there's going to be some hydrogen and some nitrogen in there. But make sure that you know that inside of magma is water gas and carbon dioxide gas and sulfur dioxide gas. Okay, another thing about magmas is that a wet magma, so that means a magma that contains water, is going to have more volatiles than a dry one. And so a volatile is anything that can turn into a gas. So water can turn into a gas, carbon dioxide can turn into a gas, sulfur dioxide can turn into a gas. And so that magmas that contain water are going to have more of these gases in them. Okay, next thing is types of magma depend on the amount of silica that they have. So it's very important that you know these words for the exam. Felsic, intermediate, mafic, and then ultramafic. So a felsic magma is going to contain the most amount of silica in it. And then the ultramafic is going to be the ones that have the least amount of silica. So the ultramafic is going to be the origin of the mafic, the intermediate, and the felsic. So inside the asthenosphere of the Earth, you have ultramafic materials. And then as these materials make their way up to the surface, they gradually change their composition. Okay. Why does magma form? So this shows the pressures and the temperatures under which substances will liquefy. So you'll notice that off to the side over here, these are going to be the low temperatures. And you'll notice that the state of the material is going to be a solid. On this side over here, this is going to be the high temperatures, and you'll notice that the state of the material is a liquid on that side. Okay, then you'll notice that up at the top is low pressures, and then down at the bottom is high pressures. Okay, and now in chemistry, there are 3 things that determine chemical reactions: temperature, pressure, and composition. So those are the 3 things that are going to control what kind of chemical turns into what other kind of chemical, and it's also going to determine what is the state, whether it's a solid, a liquid, or a gas. So notice that we've got 2 of those criteria here. We have the temperatures inside the Earth, and then we have the pressures inside the Earth. And that is going to be given by the line that looks like that. So that's the actual temperatures and pressures the deeper you go inside the Earth. And you'll notice that it intersects, so there's a point at which it does this, and then over here was when it's a liquid, and then over here is when it is going to be a solid. So notice that rocks under low pressures and temperatures are going to be solids. Okay, but then as you go deeper inside the Earth, the temperature and the pressure are increasing. Eventually it gets to this point right here, and at this pressure and temperature it liquefies. Okay, then so from here to here you're going to have your magma, and then when you get to here and you start going down, well, the pressure is so high that it's forced to be a solid. The temperature wants it to be a liquid, but the pressure is dominating, so it's a solid over here. So inside the Earth, in the crust, it's a solid. But the deeper you go, eventually you start to reach an area where the rocks turn into a liquid. So this is going to be in the asthenosphere. So this is the area of the Earth where the rocks have been liquefied, and then material from that asthenosphere is going to rise up to the surface, and then that's where we're going to get our volcanoes from. Again, here is the pressures under which igneous and rocks and magmas form, and the thing I want you to notice is decompression melting. So when you're deep inside the Earth, the material is going to be a solid. As you approach the surface of the Earth, eventually you're going to get to a certain depth at which it's going to liquefy. So this is going to be called decompression melting. We're taking away the pressure, and it's changing from a solid into a liquid once we reach this depth. Okay, then you got volatiles. So that if rocks have water in them, they are going to be more likely to melt. And so the rocks in a subduction zone, so if you recall, subduction zone is where one plate goes underneath the other plate. So at a subduction zone, those lithospheric plates are full of water because they got it from the ocean. Then as those plates dive underneath a continental plate, they're going to carry that water with them. And so that water is going to help that plate to melt easier. And so then the less dense materials then will flow to the surface as magma. Okay, and then this just shows you that it also depends on the composition of the magma. So remember, the three things that determine the chemistry of the magma is going to be its temperature, its pressure, and its composition. So this just illustrates that the composition of a magma determines whether it's going to be a solid or a liquid. So why does magma rise? Okay, first is that as the magma gets heated, it expands, and that's going to change its density. So density is the mass of an object divided by its volume. So if the volume gets bigger, so if this magma expands, then that means that its volume gets bigger, and that means its density goes down, which means that it will float up to the surface, just like oil will float on top of water. Okay, but then it's also being held down by pressure. So the weight of the overlying rock pushing down actually keeps the magma from coming up. Another thing, though, is that if you already have magma and then more magma is injected into it, well, that's going to make it more buoyant and make it want to go up to the surface. So it's kind of a competition between the pressure that's trying to hold it down and then the buoyancy, which is trying to make it go up to the surface. So what's going to control the rate that magma cools off? So the first one is conduction, so that the rocks will conduct heat through them, and then that's going to cool off the magma. Okay, then the closer you get to the surface, the cooler it gets. Okay, another thing is that if you have a thin body of magma, that's going to cool off faster than a spherical one. Okay, and then the size of the magma body, so that big blobs of magma will cool off slower than a small body of magma. Why are there different types of magma? So if we start with a blob of magma, why would it change its composition? So you need to know these 4 different mechanisms for changing the chemical composition of a magma. So the first one is going to be partial melting of the surrounding country rock. So country rock, that just means the rock that is around the magma chamber, so that the heat of the magma chamber can dissolve some of the rock that is surrounding the magma chamber, and that can mix with the magma. So that would change the composition of the magma. The second one is some crystals form, and then they will, once they are solids, those solids will then fall to the bottom of the magma chamber. So that means that up here at the top of the magma chamber, it's going to be depleted in those particular minerals, and the bottom part of the magma chamber is going to be enriched in those particular minerals. Okay, then you have assimilation of country rock falling into the magma chamber. So sometimes what will happen is a gigantic piece of the country rock surrounding the magma chamber will break off and it falls into the magma chamber. So then that's going to change the chemical composition of the magma. And then finally, 2 magma chambers sometimes will come together and mix. So you have a magma chamber over here, magma chamber over here. They come together, they mix together, and that can change its chemical composition. You should also know Bowen's reaction series for the exam. So Bowen's reaction series is going to be the mechanism by which you start with ultramafic materials. So ultramafic materials are going to be the original materials that come from the asthenosphere. And as this starts to cool off, the first minerals that can form are going to be olivine. And olivine is these isolated silica tetrahedrons with those other cations glued onto them. Okay, but then as you continue to cool down the magma, what can happen is that the olivine will begin to dissolve, and then it reforms as a different mineral. And you can see that it's going to form first as pyroxene, and then it turns into amphibole, and then it turns into mica. And then as we create these new minerals, notice that it changes from an ultramafic magma into a mafic magma, and then from the mafic magma it turns into the intermediate, and then finally it turns into a felsic magma. So notice that the felsic magma is going to have the most amount of silica in it, quartz. And the ultramafic magma is going to have the least amount of quartz in it. And then you should also notice that on the other side you have plagioclase. And so plagioclase can start as one kind of plagioclase, and then it turns into a different kind of plagioclase as it cools off. So study that diagram, and this is Bowen's reaction series. You should know that when a magma first forms, it's a particular kind of magma, and then you should know how it evolves into other kinds of magmas. So here's a comparison of olivine and quartz. So you have the olivine, which is very stable under high temperatures, but quartz is stable under low temperatures. So quartz, if you take quartz at the surface of the earth, it basically just stays quartz. If you take olivine and you put it at the surface of the earth, where it's at low temperatures, olivine will very quickly begin to decompose into other substances. So olivine is stable under high temperatures inside the earth. Quartz is stable at the surface of the earth. Olivine is going to be the first mineral to crystallize. Quartz is going to be the last one. But if you flip it around and you start to heat it up, olivine would be the last mineral to melt, whereas quartz would be the very first mineral to melt. Quartz was the one that has the large amount of silica in it, large amounts of quartz in quartz. And then olivine has the least amount of silica. Olivine consists of very simple structures, isolated silica tetrahedrons, whereas quartz is very complicated. In quartz, every one of these oxygens is hooked onto another silicon. So it has a three-dimensional complicated structure to it. Another thing is quartz is very light in color, which is going to help you to identify rocks that have quartz in them. Olivine is very dark. So rocks that have olivine in them are going to be dark in color. And then rocks that have large amounts of quartz are going to be felsic, and rocks that have large amounts of olivine are going to be ultramafic. Okay, let's take a break. And when we come back, we're going to start talking about igneous rocks.